start the recording. All right, so section 2.2 deals with the limit of a function. And again, the idea here is that by looking at the limit of the slopes of secant lines, we can determine, based on that limit, what the slope of the tangent line is. So limits are important. And there's a lot of examples that the book talks about, but I'm going to focus in the time we have on just some particular ones. So first of all, the definition of a limit. The definition of a limit. So if we, well, in the introductory example here, what they have is they have a parabola. They have a parabola, and the function is x squared minus x minus 2. That's your parabola. And I want to get it right in here. Hold on. Right, that's your parabola. And we want to investigate the behavior of the function near x equals 2. Well, they've drawn the picture of the function, and they're studying what the function does as you approach 2. So you can approach this x equals 2. Okay, you can approach that. You can approach x equals 2 from the right or the left. Okay, you're approaching 2 from the right and the left, and then you're studying what's happening with the function. Well, what's the limit of the function as x approaches 2 based on the picture here? You're approaching, whether you approach from the left or from the right, the limit's going to be 4. That's right. Excellent. Excellent. The limit's going to be 4. So as you approach 2, as x approaches 2 from the right or the left, the function approaches 4. Therefore, we can say that the limit as x approaches 2 of this function is equal to 4. Okay? That's what finding the limit of a function is. That's what finding the limit of a function is. And then they have a little bit more formal definition here for the limit of a function as x approaches a. Okay, where a is some value. Okay, so are there any questions so far? All right, great. Thank you, everyone. So, okay, well, now, if we move a little bit further here, by the way, there's different notations. You can write the limit of a function f of x as x approaches a equals L, or you can say the function approaches a limit L as x approaches a. These are two very common ways to describe what's happening. Now, on the next page here, and I'm sorry if it's a little crooked, but it's still readable. So in this figure 2, the reason it's a little crooked is when I copy the book, when I copy the page in the book off of the my copier, sometimes it's hard to get the book to be perfectly straight because of the pages and all that, but I do the best I can. All right, so in this figure 2, they're saying that the limit of the function as x approaches a, they're saying it equals L in all three cases. In all three cases. So they have here three different cases. So the first case, I think it's obvious. If you were to take your pencil and trace the function, you're letting it trace the function and approach, let x go to a. You're letting x go to a, so you're tracing the function to the left. And when you reach a, the function equals L. And then if you trace the function and approach a from the right, clearly the function equals this value, and that value is L. So the limit of the function as x approaches a equals L. Now, in the second picture, they're also saying the limit of the function as x approaches a equals L. But the second picture differs from the first picture a little bit. How does that second picture differ from the first picture? What makes it different? Let's see. Ian says the x. Well, no. Okay. So what they're saying here is you have figure 2a, figure 2b, and figure 2c. But in figure A and B, there's something different. Oh, C points out there's a dot. There's a dot. Okay, so here's what's different. Here's what's different, and you're noticing it. The function indeed is not continuous at x equals a, because what's happening here is when you get to x equals a, there's a hole right there at x equals a on the function. In other words, they have a circle. I can make the circle a little bigger, but there's a circle there. But then there's a big dot there. Well, the point x equals a is included, Lynn, but it equals this value here. It equals this value. Let me try to make this cross out. It equals this value here. But still, so when x equals a, the function value exists, but it's not like on the curve. It's below at this dot. But yet the function still has a limit, and the limit equals L. Because see, the limit is defined is if you approach x equals a from the left. Let me put it like this. Let me use my tan here. If we approach x equals a from the left, right up to the little hole there, the limit equals L. And as we approach x equals a from the right up to a, the limit is L. So the function does not have to equal L at the point x equals a for the limit to exist. The limit of the function as x approaches a equals L. They're not substituting in a for x. They're not saying that. They're not saying, I mean, f of x here is not equal to L. In the first graph, I'm not saying that right. I'm not saying that right. I don't have to clear this. Hold on. In this second picture here, f of a is not equal to L. In the first picture, f of a was equal to L because there was no discontinuity on the graph. But nevertheless, in both cases, the function still has a limit as x approaches a, and that equals L. That equals L. Okay, and okay, let's talk about C. So C, okay, how is C different? Well, C, there's no dot, and here for C, it's just a hole, which means f of a has, as Nicholas and who's the Nicholas and Anna pointed out, there's no value. F of a is not defined, and this is why I like to use the copies. Because I can write then with the little pen, and that'll be in the recording too. So f of a is not, and I'm doing the best I can here, but it's not defined. F of a is not defined, but nevertheless, the limit of the function as x approaches a is L. Okay, so for a limit to exist, all you need is if you approach the value a from the left or the right, if that value is the same, whether you approach from the left or the right of a, the limit exists. The function does not have to be defined at the value a for the limit to exist. Okay, does that make reasonable sense? Are there any questions on that? All right. Good. So of course, you know, sometimes, like if you want to look for like let me show you another example here. Okay, this example 3. Here, they say guess the value of the limit of the sine of x over x as x approaches 0. Now, is this, in this example, is the function defined at x equals 0? Is the function defined there? No, it's not. But nevertheless, the limit of the function, the limit of the sine of x over x as x approaches 0 equals 1. Okay, and you can graph the function and see that. Okay, or you could produce a table on your calculator where you can see that. But that's just, you know, a little example. Are there any questions on that? There's the graph of the function. Okay, great. Well, all right. Let's look at one more example. So they got a lot of nice examples here, but I want to, you know, focus on another example here. And this is called a one-sided limit. So in calculus, we also have what are called one-sided limits. Okay, this is actually definition 2. So they're saying here the limit of the function as x approaches a, but you see that little minus, that little subscript there, superscript minus? That means you're approaching x equals a from the left. So it's not a two-sided limit. It's not a two-sided limit. It's a one-sided limit. Similarly, you can have the limit of a function as x approaches a from the right. And if you're approaching from the right, on the superscript, you have a little plus there. That means you're approaching from the right. Okay, so a function, a limit of a function will exist as x approaches a, and it'll equal some limit L if and only if the left-sided and right-sided limits are equal. They have to be equal. Okay, they have to be equal. All right, and you know, I know that there, you know, I want to just kind of I want to just look at this example real quick. So example 7 here, hold on, says one-sided limits from a graph. So the graph of a function g is shown in figure 10. Here's the graph. Use it to state the values if they exist of the following. So the limit, like for a, the limit as x approaches 2 from the left equals 3. This means that if I follow the function and approach the value 2 from the left, it's going to equal 3. Even though the function's not defined at x equals 2, the left-sided limit will equal 3. However, if you approach 2 from the right, the limit of the function g as you approach 2 from the right is going to equal 1. That's right. So that's an example of a left and a right-sided limit. Are there any questions on that? All right. The right-sided limit, John, will always have a little superscript with a plus. The left-sided limit, the superscript will be a minus. That's right. Okay, now let me ask you this. Very good, very good. For C, they're saying, does the limit of this function g as x approaches 2, does it exist? Does it exist? That's right, it does not. That's right, excellent students, excellent. You know, Nicholas, Lynn, Sebastian, Kelvin, Anna, Sebastian, Rodrigo. Yeah, you're all right, because you're all correct, because the left-sided limit here, so what we're doing is we're looking at this C here. The left-sided limit and the right-sided limits aren't the same, and you can see it geometrically too, graphically. The limit's not the same, and so does not exist. That's right, Lynn, because they have different values as you approach from the left and right separately. Comfortable? Are you comfortable? Is everybody comfortable with that? Okay, great. Well, what I want to do is I want to stop the recording.